A modern electric car is a marvel of silence and speed. But deep within its core, an unseen battle rages. It's not fought with gears and pistons, but with electrons. A torrent of high-voltage electricity, powerful enough to run a small house, is unleashed from the battery every time you touch the accelerator. Taming this storm falls to a small, anonymous black box, the power electronics module. This is the unsung hero of the electric revolution. For decades, nearly every automaker on Earth bought this critical component from a handful of specialized European and Japanese companies. All except one. How did BYD, a company that started by making cheap knockoff batteries, decide to master the one part everyone else outsourced? How did they build a hidden chip empire from scratch? And how did that 2-decade bet turn a global crisis into their greatest opportunity? This isn't just a story about a car company making its own chips. It's the story of a radical, long-term strategy of vertical integration that created a self-sufficient ecosystem, insulated BYD from a catastrophic supply chain collapse, and is now positioning it to define the next generation of electric vehicles. This is the story of BYD Semiconductor. An electric vehicle is fundamentally a computer on wheels. A modern battery electric vehicle, BEV, has twice the semiconductor content of a traditional internal combustion engine, ICE car, a number driven by the complex systems needed to manage its electric powertrain. This trend is only accelerating. The overall automotive semiconductor market is expected to more than double, growing from $60 billion to $140 billion by 2032, with a compound annual growth rate that exceeds nearly all other semiconductor verticals. While much of the public attention goes to the brain chips, the powerful CPUs and GPUs that run the infotainment screens and enable advanced driver assistance systems, ADAS, the real workhorses are the power semiconductors. These are the unsung heroes that control and manage the flow of electricity throughout the EV powertrain, the critical link between the battery's stored chemical energy and the motor's kinetic power. For the first great wave of the EV revolution, the key component at the heart of this system was the insulated gate bipolar transistor, or IGBT. Think of an IGBT as a hyper-fast, heavy-duty electronic switch. An EV's battery stores and delivers energy as direct current, DC. But the traction motors that turn the wheels require alternating current, AC, to spin efficiently. The job of converting this power falls to a device called the traction inverter. Packed with an array of IGBTs, the inverter takes the high-voltage DC from the battery and, by switching it on and off thousands of times per second, creates a synthetic AC waveform. By precisely modulating the frequency of this switching, the inverter can control the motor's speed and torque with incredible accuracy, enabling the smooth, instant acceleration that EVs are known for. This critical function makes the IGBT module the veritable heart of the electrified drivetrain, pumping and regulating the flow of power that brings the vehicle to life. Building these high-power, high-reliability chips is an incredibly complex and capital-intensive endeavor. For this reason, the global automotive semiconductor market has long been dominated by a handful of specialized giants. Companies like Germany's Infineon Technologies and the Swiss-Italian ST Microelectronics are the undisputed leaders in power electronics, controlling a massive share of the market for automotive-grade chips. For decades, the logic of the automotive industry was simple and seemingly unbreakable. Automakers build cars, and chip makers build chips. Nearly every major original equipment manufacturer, OEM, from Volkswagen to General Motors to Ford, built their supply chains around this model of horizontal integration. They saw themselves as master assemblers, brand managers, and systems integrators, not silicon fabricators. It was a strategy that made perfect sense. Chip making requires a completely different set of skills and massive capital investments far outside a carmaker's core competency. A competitive market of expert suppliers, in theory, ensures access to cutting-edge innovation and keeps prices in check. Why would you ever attempt to build one of the world's most complex products in-house when you could simply buy it from the best? This deeply entrenched industry structure is precisely what makes BYD's story so radical. To understand why BYD broke from the pack, you have to go back to its very beginning. BYD wasn't born an automaker. It was founded in 1995 by a 29-year-old chemist named Wang Chuanfu, not to build cars, but to make rechargeable batteries. The company's initial success was built on a shrewd and aggressive strategy, reverse engineering Japanese battery designs and then re-engineering the manufacturing process itself. Instead of relying on expensive, automated Japanese equipment, BYD used a more labor-intensive model to produce batteries at a fraction of the cost. This early history established a corporate DNA obsessed with controlling the most critical, high-value components of any electrical system. It was a philosophy of vertical integration born from necessity. When BYD shocked its investors by acquiring a struggling state-owned automaker, Xi'an Qinchuan Automobile, in January 2003, the goal wasn't just to build cars, it was to build electric cars. Just 1 year later, in October 2004, the company formally established BYD Semiconductor. A year after that, in 2005, it launched a dedicated R&D department to develop its own automotive-grade IGBT. This was an audacious, almost nonsensical move at the time. The global EV market was virtually non-existent. Yet, BYD was already investing in mastering the entire power electronics stack, from the battery chemistry to the silicon chip that controlled it. The commitment was absolute. In 2008, BYD acquired Power Semiconductor, a fab in Ningbo, to bring the actual manufacturing process in-house. By 2009, it had launched its first self-developed IGBT chip, the IGBT 1.0. For more than a decade, this in-house semiconductor division was a costly, largely invisible internal project. Then, in 2021, the world changed. The global semiconductor shortage, sparked by pandemic-related demand shifts and supply disruptions, brought the entire automotive industry to its knees. While its rivals were shutting down production lines, BYD was thriving. Its long-term bet on in-house semiconductor production had transformed into a decisive strategic weapon, insulating it from the worst of the crisis. The results were staggering. The competition was crippled. Volkswagen, a global giant, saw its total production volume drop by over 2.3 million vehicles in 2021 due to the shortage. Its sales in China, its largest and most important market, plummeted by 14.1%, with 3.3 million vehicles delivered compared to 3.85 million the year before. VW's CEO admitted the company lost the ability to produce 100,000 cars in just the first 2 months of 2021 alone. General Motors faced a similar fate, with its China sales dropping to 2.9 million vehicles in 2021, and the company was forced to halt production of its most profitable trucks in North America. Factories were idled across the globe. In stark contrast, BYD surged. In 2021, a year of crisis for everyone else, BYD's new energy vehicle, NEV sales, exploded to nearly 600,000 units, a massive increase from the previous year. But that was just the warm-up. In 2022, as the shortage continued to bite its rivals, BYD's sales more than tripled to over 1.85 million plug-in vehicles. While the global plug-in market grew by a healthy 55% in 2022, BYD's sales grew by an astonishing 211%. The company that had the foresight to control its own chip supply was now running laps around an industry paralyzed by its dependence on others. The true power of BYD's strategy, however, goes deeper than just having a guaranteed supply of chips. The real, second-order advantage was the incredible flexibility that came with owning the entire design and manufacturing process from end to end. Consider the predicament of a traditional automaker like Volkswagen. Their engineers design a powertrain control system around a specific, highly validated IGBT module from a supplier like Infineon. The entire system, the printed circuit board, the software drivers, the physical housing, the thermal management, is tailored to that one component. When the chip shortage hits, and Infineon can no longer deliver that exact part, Volkswagen's production line grinds to a halt. They can't simply slot in a replacement from ST Microelectronics because it won't fit, physically or electronically. Redesigning and, more importantly, revalidating a safety-critical automotive component for a new chip would take months, if not years. BYD, in contrast, operates within a closed loop. Its automotive engineers can communicate directly and instantly with its semiconductor engineers. When a shortage of one specific IGBT model arises, the conversation changes. The semiconductor division can inform the auto division. We are short on IGBT Model A, but we have a surplus of Model B, which has slightly different performance characteristics. BYD's engineers can then rapidly redesign the power module to accommodate the available chip, or even tweak the chip's design itself to better fit the car's immediate needs. This tight integration allows for a level of agility and rapid iteration that is simply impossible in a fragmented, outsourced supply chain. This is the hidden power of its vertical integration, not just supply security, but strategic adaptability. Just as BYD mastered the silicon IGBT, the technological ground is shifting once again. The future of high-performance electric vehicles is being built on a different, far more advanced material. Silicon carbide, or SiC. Silicon carbide is a wide bandgap semiconductor. In simple terms, this means it can handle much higher voltages and temperatures while losing significantly less energy as waste heat compared to traditional silicon. This superior performance translates into several game-changing benefits for electric vehicles. First is efficiency. SiC-based inverters can reduce power losses by as much as 80% compared to their silicon IGBT counterparts. This directly translates to a 5 to 10% increase in vehicle range from the very same battery pack, a massive gain in an industry where every mile counts. Second is the enablement of high-voltage architectures. SiC is the key that unlocks the industry's shift to 800-volt battery systems. Higher voltage allows for dramatically faster charging times, capable of adding hundreds of miles of range in under 20 minutes. It also reduces the current needed to deliver the same amount of power, which in turn allows for lighter and cheaper copper wiring throughout the vehicle. Finally, SiC offers superior power density. Because SiC components run cooler and more efficiently, they can be made much smaller and lighter. This reduces the overall size and weight of the powertrain, giving engineers more design flexibility and contributing to a lighter, more efficient vehicle. If SiC is so revolutionary, why isn't every car equipped with it? The answer is that manufacturing it is incredibly difficult and expensive. The process begins with growing a SiC crystal, or boule. This is done at extreme temperatures, often exceeding 2,200 degrees Celsius, in a painstakingly slow sublimation process that can take weeks. The resulting material is one of the hardest on Earth, making it incredibly challenging to slice into thin wafers without introducing microscopic defects. These defects, known as crystalline stacking faults or micropipe defects, can render a chip useless. This entire process suffers from very low yields, meaning a large portion of the produced material is discarded. The result is that a single SiC semiconductor can cost up to 8 times more than its silicon equivalent. Recognizing silicon carbide as the next critical battleground for EV supremacy, BYD is repeating its IGBT playbook, but on a much grander and more expensive scale. It was the first domestic Chinese company to successfully mass-produce a SiC power module for a high-end EV, its flagship Han sedan. Now, it is pouring billions into building a complete, in-house SiC supply chain to secure its future. This includes a massive $1.4 billion, 10 billion RMB project in Shaoxing, dedicated to power device and sensor manufacturing. In Ningbo, the company is building a new SiC Power Semiconductor wafer manufacturing line with a planned investment of 730 million RMB and a target capacity of 20,000 wafers per month. And in its home base of Shenzhen, it is investing 214 million RMB to expand its SiC epitaxial wafer production line to a capacity of 18,000 wafers per year. This massive capital outlay reveals a deeper strategic calculation. BYD's investment in SiC is not merely about gaining a technological edge. It is a crucial defensive maneuver to prevent becoming dependent on the very competitors it seeks to defeat. The global SiC market is currently dominated by a small number of players, including STMicroelectronics, Wolfspeed, and ROHM. These companies are also the key suppliers to BYD's global rivals, most notably Tesla. If BYD were to rely solely on these external suppliers, it would find itself competing for the same limited production capacity as everyone else, completely erasing the supply chain advantage it painstakingly built with IGBTs. Worse, in a future shortage, these suppliers might prioritize their established relationships with Western or Japanese automakers, leaving BYD vulnerable and at the back of the line for the most critical next-generation component. Therefore, building its own SiC capacity is an existential necessity for BYD to maintain its vertically integrated strategy. The company is spending billions today to ensure it is not at the mercy of its competitors' suppliers tomorrow. A strategy of radical vertical integration is brutally expensive. In 2024 alone, BYD's research and development expenditure reached a staggering 54.2 billion yuan, approximately $7.5 billion, a figure that far exceeded its net profit for the year. While the company currently boasts strong cash reserves, this level of sustained capital expenditure, especially during an intense EV price war in its home market of China, puts immense pressure on profitability and is a key risk highlighted by industry analysts. Controlling your own destiny comes at a steep price. This leads to a fundamental question. Can a division within a car company truly out-innovate hyper-specialized global leaders in the long run? Companies like Infineon, STMicroelectronics, and Wolfspeed dedicate their entire existence to advancing power semiconductor technology. They serve hundreds of clients across dozens of industries, from automotive to industrial to consumer electronics, giving them broader market insights and greater economies of scale. BYD's R&D, while massive, is primarily focused on its own automotive needs. There is a tangible risk that its technology could become too insular, optimized only for its own platforms, and eventually fall behind the cutting edge being developed by dedicated market-facing players. Some analysts argue that despite its progress, China's overall semiconductor industry remains generations behind the world leaders in the most advanced technologies, a gap that a single company, no matter how ambitious, may struggle to close on its own. This tension between long-term strategic investment and short-term financial performance was thrown into sharp relief by the saga of BYD Semiconductor's planned IPO. In 2021, BYD announced its intention to spin off and list its semiconductor unit on the stock market, a move that would have unlocked its value, which was estimated at over 10.2 billion yuan. However, in a surprise move in late 2022, BYD abruptly terminated the listing plan. The official reasons were complex, but the strategic logic is clear. An IPO would have brought in public shareholders, and with them, the relentless pressure for quarterly profits and rising stock prices. This is fundamentally incompatible with a company in the midst of a massive, multi-year, multi-billion-dollar capital expenditure cycle to build out its SiC capabilities. These enormous investments are designed for a payoff 5 to 10 years down the line, and they crush short-term profitability. Public shareholders would almost certainly have revolted, demanding cost cuts and a swift return to profitability, which would have killed the long-term SiC vision in its cradle. By keeping the unit private and under the full control of the parent company, founder Wang Chuanfu can continue to fund the ambitious strategy without answering to the whims of the public market. The IPO will likely be revived, but only after the heavy investment phase is complete and the division has matured into a stable, profitable entity. Finally, it is crucial to acknowledge that even for a powerhouse like BYD, vertical integration is not a magic wand that eliminates all dependencies. The company's mastery is a spectrum. While it has achieved a high degree of self-sufficiency in silicon IGBTs, the transition to SiC is a work in progress. Recent industry reports indicate that BYD still sources SiC bare dies from external suppliers, including Bosch and ST Microelectronics, for some of its power modules. This highlights a key reality. Scaling a complex new technology takes time, and even a vertically integrated giant may need to lean on the expertise and capacity of the broader ecosystem during the transition. Its integration is a powerful strategic tool, but not an impenetrable fortress. The story of BYD's rise cannot be understood by looking at its cars or its chips in isolation. Its success is the product of a powerful, self-reinforcing symbiotic loop between its automotive and semiconductor divisions. The auto business provides a massive, guaranteed internal market for the semiconductor unit, allowing it to achieve economies of scale, battle-test its products in a demanding real-world environment, and fund further R&D. In turn, the semiconductor division provides the auto business with a secure supply of cost-effective, customized components, granting it a decisive competitive advantage in cost, agility, and supply chain resilience that its rivals simply cannot match. Each half of the empire makes the other stronger. Perhaps the most significant strategic evolution in recent years has been BYD Semiconductor's deliberate push to sell its products to external customers. What was once a secret weapon, exclusively for internal use, is now being offered on the open market. The company now supplies its chips to a growing list of other industrial and automotive players, including Chinese vehicle makers like Socon and Yutong, and industrial controls companies like Innovance and Huichuan Technology. This move fundamentally transforms BYD Semiconductor from a strategic internal supplier, which operates as a cost center, into a market-facing competitor that must operate as a profit center. This shift serves several critical purposes. First, it creates a new and potentially massive revenue stream, helping to offset the enormous capital investments in R&D and new fabs. Second, it forces the division to compete head-to-head on price and performance against the global leaders, preventing the kind of technological complacency that can arise in a closed ecosystem. Finally, it positions BYD not just as a car company, but as a core technology provider for the entire Chinese EV industry, dramatically increasing its influence and market power. The future of the global auto industry is shaping up to be a grand battle between two opposing industrial philosophies. On one side stands the traditional model of horizontal specialization, where automakers act as orchestrators of a complex web of expert suppliers. On the other side stands BYD's model of radical vertical integration, where control over critical technology is paramount. BYD has placed a multi-decade, multi-billion-dollar bet that in the volatile, fast-moving, and strategically fraught world of electric vehicles, the company that controls its own destiny by controlling its own supply chain will ultimately win. The global chip shortage of 2021 proved them right for the age of silicon. Whether they can repeat that stunning success in the coming age of silicon carbide will not only determine the future of BYD itself, but may very well redefine how the cars of the future are built.